The ratio test is the last of the major tests that we can use to determine whether a series converges or diverges. This test is particularly useful because you can use it on series that have both positive and negative terms, or on series that are all positive or all negative terms. Unlike many of the tests we have that require that the series have entirely positive terms, it works by comparing a series that we're interested in to a geometric series, and essentially saying if that series behaves enough like a geometric series, then we can use the facts that we know about geometric series to determine whether that series converges or diverges. Here's how it works. Given a series, a sum as n goes from 1 to infinity of an, we'll compute the limit of the absolute value of the ratio of each term over the previous term. So that's the limit as n goes to infinity of an plus 1 over an. And take the absolute value of that, find the limit as n goes to infinity. Let's call that L. So you're essentially saying, what is the ratio of the next term divided by the previous term in the series? If that limit ends up being less than 1, then that means your series is like a geometric series where the common ratio r is less than 1. Actually, the absolute value of that r is less than 1. And we know that in that case, the series converges. So we can say in this case, our series converges absolutely. If that limit ends up being greater than 1, then, just like for a geometric series with a common ratio being greater than 1, the series diverges. If that limit equals 1, then what that tells us is the ratio test is actually inconclusive. In the case of a geometric series, we know that if the r is equal to 1 or negative 1, then the series would actually diverge. But for a series that is not a geometric series, sometimes that ratio can approach 1, and the series may still converge, or it may diverge. It depends on the series itself. So we'll have to use a different test in that case. Let's try an example. Let's look at the sum as n goes from 1 to infinity of the expression negative 2 to the n times n squared, all divided by n factorial. Now this is kind of complicated, but I've included this one so that we see the full range of what the ratio test will do for us. First thing to note is this is an alternating series. Because we have negative 2 to the n as part of the expression there, and that means that every time n increases, you're going to swap from positive to negative. Every power, if you put even powers on the negative 2, you'll get a positive number. Put odd powers on there, you get a negative number. So our terms are going to alternate positive, negative. The first term actually is going to be negative because n starts at 1. So we'll have negative 2 times 1 squared, which is 1. All right, 1 squared, over 1 factorial. So that's just going to be negative 2. Plus 2 squared times another 2 squared over 2 factorial. So 2 squared is 4, 2 squared is 4, that's 16, but 2 factorial is also 2. That's going to give us 8. Now, negative 2 to the third power, that's minus 2 cubed times 3 squared over 3 factorial. So let's see, we've got 8 times 9 divided by 6. 3 factorial is 6. So we're going to end up with, 8 times 9 is 72. Divided by 6, we get 12. So minus 12. So far, it's looking like our series might be diverging. Certainly the terms seem to be getting bigger and bigger. But let's see what actually happens as n goes to infinity. The next term is plus. Keep going. So let's try the ratio test and see what kind of result we actually get. Note, by the way, that because this is an alternating series, we could actually use the alternating series test here, and we might be able to determine that the series converges using the alternating series test. We need to check two things. Check that the limit of the terms is 0, and then also check that the terms are decreasing, at least for large enough values of n. So we already saw that some of the terms, the size of the terms, is increasing early on, but as long as, say, after the 100th term, then the terms start to decrease, then you'd know that your series converges, if both of those are true. But it wouldn't tell us whether the series converges absolutely. And we'd like to know that, so let's check that. Let's try the ratio test. So we're going to compute this L, this limit here. And this is the limit as n goes to infinity of the absolute value of an plus 1 over an. Now the ratio test is pretty useful, but the one thing that it does require is good algebra skills. So let's make use of those here. Let's fill these in. So we're going to get the limit as n goes to infinity of the absolute value of, all right, an plus 1. That is going to be negative 2 to the n plus 1 times n plus 1 squared over n plus 1 factorial. Now, that's all just my an plus 1, my next term after an. All I did was fill in the formula for the an's there, but replace the n with n plus 1 everywhere that I saw the n. Now, big division bar, because we're dividing this by an entire fraction, I'm just going to fill in an now, and that is just negative 2 to the n times n squared over n factorial. Extend these absolute value signs here. That is our expression. Don't panic. What we have here is a fraction divided by a fraction. We know how to handle that. That's going to give us the limit as n goes to infinity of the absolute value of what? Well, a fraction divided by a fraction, that's actually multiplication. In fact, you could skip the step that I just wrote down and go straight to the multiplication step, because what we're really going to have here is an plus 1 times the reciprocal of an. So we're going to have negative 2 to the n plus 1 times n plus 1 squared over n plus 1 factorial times the reciprocal of an. So that's going to be n factorial over negative 2 to the n times n squared, all inside the absolute value. So let's try to simplify this and actually compute this limit. So I made a little space here. So what we need to do now is realize, well, we're multiplying two fractions. That means that we're multiplying all the things on the top, and we're also multiplying all the things on the bottom. And we can rearrange the order of those things any way we want to. What I'm going to do is I'm actually going to group factors of the top and factors of the bottom that are related. This is a pretty common trick to use when you're doing the ratio test. So there's really kind of three components to the expression that forms the terms of this series. We have the exponential part, the negative 2 to the n. We have the polynomial part, the n squared. And we have the factorial part, n factorial. And each of those expressions, because we had an plus 1 over an, each of those parts is going to give us a factor on the top and a factor on the bottom. And what I'd like to do is group those all together. So here's what I'm going to do. This equals the limit as n goes to infinity of the absolute value of, let me get my exponential parts here together first. So I've got negative 2 to the n plus 1, my big division bar here, over negative 2 to the n on the bottom. Then we also have the polynomial part, the n plus 1 squared, or n squared. So we have n plus 1 squared on the top, and we also have n squared on the bottom. These are all being multiplied. And then we have the factorial parts here. So that's times n factorial on the top, and times n plus 1 factorial on the bottom. And then we have the absolute value sign there. Let's handle each of these parts separately. So I'm going to just look at negative 2 to the n plus 1 over negative 2 to the n. just over on the side here. I want to look at each of these things separately. So negative 2 to the n plus 1 divided by negative 2 to the n, well, that means I'm going to multiply negative 2 by itself, n plus 1 times, and then divide that by negative 2 multiplied by itself n times. What am I left with? Just negative 2. So I can fill that in. This is going to equal the limit as n goes to infinity of the absolute value of negative 2. I'm actually going to leave that n plus 1 squared and the n squared on the bottom alone for now. I want to focus on that last bit, the factorial bit. So we've got n factorial over n plus 1 factorial. Now the thing about factorials is that you are multiplying by more numbers if you have a bigger factorial, but the numbers themselves are also bigger. In fact, n factorial is the product of all the numbers from 1 up to n, right? 1 times 2 times 3, etc., up to n minus 1 times n. N plus 1 factorial is the product of all of those numbers, including n, and then times n plus 1. Right? 10 factorial is 1 times 2 times 3, etc., times 9 times 10. And 11 factorial would be all those numbers times 9 times 10 times 11. So, n plus 1 factorial is actually the same thing as n factorial times that last number, n plus 1. And on the top we have n factorial. So these guys cancel out. And we are left with not n plus 1, but 1 over n plus 1. So we've got a 1 over n plus 1 here. And now you see why I left that last part, the n plus 1 squared and the n squared alone for now. I'm going to put those back in now. N plus 1 squared over n squared. Hard to simplify that blue part by itself. Let's end that absolute value sign. But what we can do is say, well, I've got n plus 1 squared on top and n plus 1 on the bottom. I can cancel those and have just n plus 1 on the top. So now, let's just clean this up a little bit here. We've got, let's see, well, the limit as n goes to infinity of the absolute value of 2. Now I can actually address these absolute value signs here. N is approaching infinity, which means that n is going to be a very large number. So n plus 1 is positive, and n squared is positive. Negative 2 is negative, but if I take the absolute value of that, I'm just going to get 2. So we've got 2 times n plus 1 over n squared. Now at this point, we're just taking the limit of a rational function as n goes to infinity. This is easy. We know how to do this. You can do this the more rigorous way by dividing the top and bottom by a power of n. I would say divide the top and bottom by n to the first power in this case. But we're actually experienced enough now that we can justify just doing this the quick way, which is to note the top has degree 1. The bottom has degree 2. Since the power on n is bigger on the bottom, we know that this limit is going to be 0. So, what do we conclude from this? Well, our L, our limit of the one term over the previous term, ends up being 0. What that means is, as you look at these successive terms, as you go further and further and further down the line, not only are the terms themselves approaching 0, but each term is becoming a tinier fraction of the previous term as you go down. Now, we wrote out the first few terms, and it didn't seem like that was happening. We had 2, and then we had 8, and then we had 12, and so on. And the reason it is because expressions like negative 2 to the n and n squared seem a lot bigger than n factorial when n is small. But when n is large, n factorial ends up being a lot bigger than 2 to the n or n squared. And we end up with an expression where the denominator is much, much bigger than the top. And we end up with terms where the limit of one term over the previous is approaching 0. So what this tells us is this series is in fact converging. In fact, it converges absolutely. Since our L, which equals 0, is less than 1, this series converges absolutely. So again, we could have tried to use the alternating series test here. That actually would have worked if we'd been very careful about it. We could have actually used the alternating series test, and we would have determined that the alternating series does converge. But that wouldn't have told us whether the series converges absolutely. In other words, whether if you take the absolute value of all the terms, do you still get a convergent series? The answer is actually yes, you do, which therefore implies that the original series, which has positive and negative terms, also converges.